means in the Sega picture, we're cutting along a circle. Circles. And associate the circles with some bulk Hilbert space. And for this bulk Hilbert space, we can also associate some bulk Hamiltonian. And do the spectrum resolution for this bulk Hamiltonian, we mean the bulk bootstrap. And the similar terminology is called boundary bootstrap. Some terminology. For the boundary bootstrap, we mean in the Sega picture, we cut along arcs, and we associate some boundary Hilbert space. And maybe some H here and H plus here. And for the bulk Hamiltonian, I use H. And the boundary Hamiltonian. So pictorially, this corresponds to some cutting along some circles, and this corresponds to some cutting along arcs. Okay, this is just some terminology of this bulk bootstrap and boundary bootstrap. So even in the surface with boundaries, we can do the
this is group which ends on the bottom.
Yes, arcs. I call it arcs. In the first part of my talk, I will briefly review the boundary Liouville CFT. This is done by for the disk case. This was constructed by and with Marcus. I will say the most technical issues is many due in this paper, and later Guillermo for the Daniel's case. Basically, it's just generalize this construction. So there is no essential technical development. And then later I generalize this for the general surface. Here I fix sigma g as a remaining surface with real analytic boundary. Recall the Liouville action. I put a B here, means the boundary version of Liouville action is given by the phi G. G is the metric, phi the field. K is the Vichy curvature, and
maybe you can lift up a little bit blackboard so we see the
there is additional boundary term. Baptiste also introduced this object yesterday, and it has the critical point of this action has some classical geometry meaning, which uniformize your surface, some singular type, some metric in your surface. Give you a uniformization. This is the Vichy curvature, and this is geodesic curvature. Here I act the parameters I use. Here Q equal gamma over 2, gamma equals 0 and 2. And mu is a non-negative called bulk cosmological constant. And mu B is also non-negative, and it's piecewise constant. The first step is to make sense how to introduce this kind of Liouville CFT. You basically want to introduce some measure on all the map from sigma to R.
Can you remind us what the geometric mean of solution of motions as a critical point with the bound?
Okay. So if I take Q equal 1, say classical geometry. If I take for Q equal 1, and you do the variation on this phi, and then the K phi star something like
Sorry, what is SL? Is the second term?
At sigma.
And phi equals, you wrote phi L.
Phi star. The critical point is phi star. This is a critical point.
What is 5 star?
We solve this. We do the variation on this functional and found the critical point.
Okay.
This phi star uniformizes this measure.
Okay.
Okay. Maybe they are up to some pi or some constant. Here I don't remember. So. Okay. This is the classical geometry picture, and now we want to introduce for any. We want to define this. We want to make sense of this.
I beg your pardon. Can you read this formula? So it's Gauss curvature inside for the magnitude equal phi star G equals minus mu. And the second formula I can't even see. This is boundary.
Geodesic curvature. This is Vichy. This is geodesic. We want to make sense of this measure for all positive functional, for example. To define this, we need to introduce some some tools in probability. The first I want to introduce is the Gaussian free field. The Gaussian free field is formally you can view as some Gaussian process that the to formally view this, I will not expand how to introduce this in some soft-level space. I just said that here for a surface with boundary, I consider the Laplacian with Newman boundary condition, and I found it's a green function, and I introduced the Gaussian free field as the expectation of this the covariance is given by the green function. Here I also fixed the normalization set at the xg, because the green function is only defined up to constant. I fixed this normalization. This is the Gaussian free field. So basically, because we have this gradient phi square term, we want to view the phi as some Gaussian field. And the point is we need to make sense this exponential gamma phi measure. Now we introduce the, how should I need first to use this backboard. I found the Gaussian multiplicative chaos. Here I define there are two kinds of Gaussian multiplicative chaos. Compared to the bulk case, there is only one, but here we have two. There is a bulk Gaussian multiplicative chaos we call the bulk GMC. It is introduced as, I use this notation. You see this. For GFF Here I use H because later I will use some variant of this actually. For example, it can pass some deterministic function for GFF with H. I use this later. And the boundary GMC measure. I use P here, means boundary. Here, this is the volume form induced by the metric, and this is the boundary measure. And compared to the bulk case, for example, we can.
Baojun, can you write a little bigger?
Okay.
But do you need the left blackboard?
Because the left board is prepared for something.
No, but maybe you can erase this one and write push and up, because I can see, you're writing, I can see what you're writing. Because it's
use this notation. The first remark is the total the bulk GMC measure. If you compute its expectation, is finite if and only if gamma square smaller than 2. This can be shown by using some properties of green function. So this actually brings a lot of issues when we study the boundary Liouville theory. But the existence of these two GMC measures can be obtained in the full range, like gamma smaller than 2. Let me finish. These two measures. But when we study boundary Liouville CFT, because this kind of expectation is finite if and only if gamma square smaller than 2, we meet a lot of problems. For example, our general boundary bootstrap only holds for gamma smaller than square root 2. Because this kind of issue. Okay. Now, when we define this, when we introduce, after we introduce these two measures, we can make sense this last integral. And the observables we are interested in is now I will introduce something called primary field. The primary field is introduced as there are two different types of primary fields. You can have since you are surface with boundary, you have some boundary primary fields and also bulk primary fields. Here I use x and it's the coordinate s.
Baojun, sorry, but it's hard to read from far. Can you zoom? When you write?
So should I
just write bigger?
So here we introduce the Liouville field. And the epsilon is some kind of regularization because phi is only a distribution. You need to regularize this. For example, I can take some geodesic circles. On the boundary, I take some geodesic circle and I only average on this arc which belongs to the surface. Okay. And when we take f phi epsilon, the functional, as a product of the. Suppose there are m bulk insertion and mb, b here small b means boundary. Boundary insertion. If I define the Liouville path integral for this particular type functional, I will use a notation the limit exists, and the theorem is the limit for the separate bound, for alpha in the alpha beta in the separate bound, like alpha I. And all these alpha I and beta j smaller than q. And also the this functional, this one we call the correlation function. We call it the correlation function. And the correlation function satisfies some nice properties called one is where anomaly means if you change the metric to some metric G prime, which is conformal to G, you can explicitly compute the factor which is given by the Liouville action. And another thing is called diffeomorphism invariance, which means this whole correlation function is invariant under isometry. Okay. Now I expand the construction of the boundary Liouville CFT, and the next part is the goal is to compute all this correlation function use bootstrap method. The first step is to compute the structure constant. This part is already mentioned by Xin yesterday. I just connect what is a basic structure constant from the boundary Liouville CFT. There are two kinds. One is the for disk with 3 mark points, and you put some boundary primary field here. Like I put a beta 1, and the location is S1. But since we have some real anomaly and diffeomorphism invariance, we can already fix this like 1 minus 1 and I, something like this. And we also need to introduce the as I mentioned here, the mu b is only a piecewise constant. So I can choose a different boundary cosmology constant here. Here is mu b1, and this is mu b2, this is mu b3. And this was computed for mu equals 0 case by Remy Zhu. And for mu larger than 0 case by Maurice Ang, Remy Zhu, Xin Sun, and as explained yesterday, this this formula is given by up to some factor. Is given by the CG symbol. Some principal representation for module double of UQSL2, and also coincide with the fusion kernel of the.
Baojun, you are writing smaller and smaller. You need to keep the same size.
Can you reduce the size even more?
the fusion kernel for Liouville CFT, and
But can you comment on this correspondence? Shin-san was talking about this very mysterious formulas.
You mean how to
How
prove?
left-hand side computed for 6J symbol, how the parameters match.
Oh,
And
okay.
he said this is only when mu equal 1. Can you give us general statement?
Okay, I will answer your question. So here, this is arbitrary mu,
Yes.
but we know the case. This is the bulk cosmology constant. We know that for the arbitrary mu, this one is equal mu. With mu equal 1 case.
Okay, and how to calculate this through 6J symbol? Can you comment on this?
And here if I parameter, for example, now I can fix mu equal 1. Maybe I should write it another. And I reparameterize this mu b equal so for each mu b I use mu bj. I use this sigma j to parameterize this mu bj. Then this one.
Sorry, what's written here? Pi gamma divided by 2, and the brackets, I don't know what's the symbol.
This is the sigma as a function of
Sigma.
sigma.
No, not 6G.
It is sigma, and it was a joke that this is not 6J.
I can associate this 3-point function with the tetrahedral. Like I draw this picture here. I put beta 1, beta 2, beta 3. They share the same surface. And so here you see that the beta 2, the opposite arc of the beta 2 is mu 1b. I associate a beta 2 is a sigma 1, and the beta 1 is a sigma 3, and the beta 3 is a sigma 2. And I use this, the correspondence is this 6G symbol. Like,
Yes.
but my notation and Shin's notation differ by 2. For me, the spectrum is Q plus IR. Because here otherwise I need to divide the 2 on this kind of relation. Beta 3 sigma 2. Okay. This is the 6G symbol, or we usually call it the B6G symbol, or boson tensional 6G symbol.
Can you comment on geometrically intuitive explanation of this? I guess this is when you try to compose this.
Yeah, but to give some geometric meaning of this, why this 3-point function is related to the 6G symbol or the fusion kernel, I need to first talk about the boundary bootstrap.
Excuse me, and well, so far everything depended on the metric G.
Yes.
And on this picture,
Yeah, I mentioned in the 3-point case, the metric. So here, the boundary 3-point function, the complex structure is just 1 point, and for this correlation function, it has very nice properties. If you conformally vary this metric, you can get a very simple factor. So it's called a Weir anomaly.
but still you need to fix some particular G here.
Yeah, I can fix. So if I fix some G, I will get some trivial factor here, like depend on G. But the structure constant is irrelevant to G. For example, I can fix some.
But you need to fix this constant because the 5-term relation is not homogeneous. You cannot multiply all
If
symbols by constant.
The simplest way to fix to represent this structure constant is use the half arcane model. I choose a conform map here, and I put a beta 1, beta 2, beta 3 here, and I put the 3 point located at 0, 1, and infinity, and I use metric G equal.
And that gives a good normalization.
This exactly give you this formula.
Sorry, what's it in dz divided by?
This is just a metric you obtained by glue two fat disk.
Which means max.
Max.
It's in probabilistic notation.
The max between modulus and z.
This metric.
Max.
Z and 1. The absolute value of Z and 1.
And z is in upper half plane.
Yes.
Yeah, Z is in half up.
So it is not smooth.
No smooth.
No, it's a pancake if you want.
What is?
You have a. So you know, if I consider
It's invariant by inversion.
this is the metric, the Euclidean metric on the unit disk. I use a map H Z to 1 over Z bar. I pull back this metric. This metric will change from a dz square to some dz square for Z power 4.
How geodesics looks like?
It's just a two flat disk, you glue them together. And the curvature is concentrated on the sphere. This is a sphere, and the curvature is concentrated on this circle.
So you saying that so this is on upper half plane metric.
Yes.
And this is on a sphere, so it's.
Yeah, you restrict this metric to this.
So you're saying that if you reflect this metric with respect to the real axis, then you'll get that metric which has curvature.
No. It's, here I define this metric on this half up.
No, but he's right.
He's right,
Reflect,
yeah.
This is what you mean.
Reflect on real line. Real line it doesn't change this metric.
No, but if you glue.
Your right picture is on the two-dimensional sphere, and your
Yes.
left picture on upper half plane.
Yes.
And you said they're the same.
You restrict this metric to this half up. So it's like this metric also symmetrical on this Z to Z bar.
Will you please make this picture again?
Let me see no, I go to the part 3. Part 3 is the bootstrap. The bulk bootstrap in the. Here I will explain how to compute the goal is to compute here I have an annulus with the surface is the annulus and the metric is a flat metric on this annulus. The inner radius is given by Q. Q is a real number. Then I want to the goal is to compute the partition function of this surface. Due to this reason, this partition function is actually infinite. And how to compute them is I consider a variant of this function. The rigorous definition is this rigorous definition of partition function. Is this one? Somehow I reweighted both boundary by their boundary GMC measure. Then we first recognize this boundary field and show this limit exists. And the result is this one can be written as some integral. Yeah. Oh, okay. I forgot there are two different kind of boundary structure constant. I only explain one here. I need to explain another one. So here, let me first finish this formula, then I introduce another boundary cosmological constant. You do the integration over P along some site. I will explain this is called Liouville spectrum, and divided the Dedekind eta function. Here, is called the Liouville spectrum. Now I expand the function G. Function G is also a structure constant. I only use the backward in this region. Fine.
Sorry, what is G?
I will expand now the G. The structure constant here I only introduce one of the structure constant. Another structure constant I haven't defined yet.
But you don't use this measure soon, wrote yesterday?
Which measure?
Absolute
Volunteer measure of this
No. No, this measure. Just a dp. This is still in the part 2. There is another structure constant. You have one bulk insertion and one boundary insertion. And this for bulk insertion, we usually use the notation alpha, and the boundary insertion, we use the notation beta. And the cosmological constant over here we put is mu b. And the mu b is here is indeed a constant. So I say it's piecewise a constant because it's only one insertion, it's just a constant. This function is called the Haussmann formula. And it's also a very complicated formula. I will not give you explicit form here.
But this is the most important?
The most important thing is this one corresponds to the modular kernel of torus 1.1. This is introduced in the NASA talk. This function, the modular kernel is was introduced in the NASA talk by Promi. This formula coincides with the modular kernel of the torus 1.1.
Why is it related to torus 1 point?
This can be expanded by using Bootstrap method. Now I'm giving some basic setting, then I show how to justify the two facts, like model kernel towards 1 point block. And this also corresponds to the fusion kernel of 4 point sphere conformal. Here, the boundary cosmology constant here, because you have inner and outer boundary, we can put like mu b1 here and mu b2 here.
And what is the reason of putting minus I pi in the second G?
Q minus IT.
So it's kind of conjugate.
Yes, conjugate. Because when we do the bootstrap, we need some orientation, and you compute one side, you use the incoming orientation, another side is outcoming. Somehow you need to change this Q plus IP to Q minus IP.
The formula looks symmetric, not this possibility.
For example, if you take a complex conjugate of Q plus IP, you will get some Q minus IP. Because it's actually a homomorphic function.
And from the spectral resolution. So if we transform, you have exponential IPC and exponential minus IPC.
Sorry, and why do you set beta to gamma in this integral? You take a special value of this.
Yeah. Because I awaited the boundary GMC measure. So you can view this as some insertion. Maybe I use this notation. This beta over 2 is G alpha beta.
But don't we expect to have the 0 so that you're integrating, in fact, 1 point?
Yes. This also. So there are some degenerate case of this two structure constant. For example, you can consider some 2-point function here. And in this case, you can also consider there is only one bulk insertion. And this GQ plus IP gamma is like a degenerate case, like a Q plus IP without a boundary insertion, or you can give some uniform boundary insertion. I put a boundary GMC measure here, but as I expand, this function has a very nice property. For example, it's rotational. You can imagine the rotation. You do some rotation, the value doesn't change, so you still get this the GQ plus IP gamma. So this is some degenerate case, also called FZZ formula. This one. Okay. No, to explain how to do the bootstrap, I need to record some terminologies. In the bootstrap, our coordinate space is some Sobolev space on the unit circle. Maybe that's unit circle. So for any phi, you can do some. I use this notation. For any field on the unit circle, you can expand. You have to do some Fourier transformation. You collect all this coefficient phi and view this as some coordinate space. And for the Hilbert space, it's like the Hilbert space you define as the L2 functional on this this as small with some measure. Basically, this measure makes this coefficient is.
So you have some h with some upper index, I don't know, s or something. This is your number which is less than 0. I just trying to read.
Okay.
H s of s.
Yeah, S is the unit circle.
And another.
The index of Sobolev.
How you call it? What's the letter?
S.
S.
You can take S equals by this one if.
Okay, I oh, my last one.
And this is less than 0.
So first I have some field on the unit circle. I want to calculate all its coordinate is given by this phi n. Then I want to consider some functional on this coordinate. I introduce another space. In this space, d mu 0 is a product measure on C and this DC is a big measure, and the PT is basically make this phi n is a complex Gaussian. Sorry, it is a complex Gaussian.
Complex Gaussian.
Complex what?
Gaussian measure.
Oh, Gaussian.
Yeah, it's we want to make all its coordinates a complex Gaussian.
So there are just two real Gaussian.
Yeah, there are two real coordinates. Actually, this corresponds to, in the bulk case, we have homomorphic Virasoro algebra and anti-homomorphic Virasoro algebra. And I introduce the notation of the. First, I do the Hamiltonian and eigenstate. As explained in him and Guillaume's talk, the Hamiltonian in the Seagull picture correspond to some annuals with two Dirichlet boundary condition, and if you glue these two annuals together, you get another annuals. This corresponds to the Hamiltonian in the bulk case. And for the eigenstate, you can imagine is some amplitude correspond to the disk with one mark point. Five. And the spectrum resolution is how you diagonalize this space by this eigenstate. You need to use study some spectrum theory on this Hamiltonian, and you will get a family of eigenstate labeled by Young diagram. This nu and nu tilde are Young diagram, and use the label mu here. So this one is the generalized eigenstate of this H. And for any two elements in H, if you want to compute its inner product, you can use this eigenstate to diagonalize its inner product. Here in this case, since we have annuals here, and I do the Seagull cutting along some circle, so I do the bulk bootstrap. I only use the thing here. I use the bulk bootstrap. I do a cutting here. Then this annuals is separating into two annuals. You get a pairing with this with some boundary field here, and another one. In this Hilbert space. Then to get this formula, the goal is just to compute the pairing of the next step is to compute the pairing of this one. This is mu B1, mu B2. With this psi, alpha, mu, and mu tilde. And as explained by Guillaume and his talk, this one can be, this is some descendant states, but you can use Virasoro algebra act on the primary state. This is the some Virasara representation in the in this space in H called the Liouville Virasara algebra. We want to compute the pairing of this one with this one.
No, you're missing a tilde on the.
Oh. Then the result is like this. You can prove this. This is called compute this. So this basically will factorize as this structure constant, which is the pairing of this state with the primary eigenstate phi alpha, and times some polynomial or some rational function depend on conformal dimension of this Q plus IP. This is called Ward identity. The proof of this now can be using the variation of semigroup to a semigroup. Remember, there is also always a boundary GNC layer on this circle, like and gamma B on this circle. Otherwise, it's not finite. It's not Hilbert-Schmidt, or the kernel is not L2. You cannot use the bootstrap method to compute it. The proposition is just this one. If you're pairing this with and for some suitable test function, I will not write it. This is 0. I think in physics literature, this is somehow called a conformal boundary state or Cauchy boundary state. Like if you input some L minus n here, you get Ln tilde. To show this, you just use the method explained by Himi and Guillaume. You use some semigroup variation, but in this case, your vector field should preserve the boundary. And then this will give you some relation between L minus n and Ln tilde.
This must act on something.
You can act on f, for example. Some f. F is I didn't introduce the domain of the some quadratic form, but f is something. And all the eigenstate is beyond to you can act on all the eigenstates. I said next for the eigenstate. From this, you can easily compute from this you can easily compute this one, because once you have L minus n here, you change from n. Let's say n. This is true for arbitrary n. Let's say for n larger than 0, this is some descendant, but here you from L minus n actor here you can change to the Ln actor here. Then it will kill some L tilde. And basically, if you do this computation, you will get the Shapovalov form.
Q is the size of the annulus. Q.
Q is the size of annulus. And here I do some cutting here. This is not important, but I choose the square root Q. And the whole annulus, the model of whole annulus is Q, and here is the small square root Q. Then this gives you some Shapovalov form. And then you use the spectrum resolution, you put everything here, you get this kind of factor. That's why this factor is so simple, because you just use the sharp power form. And another thing to remark is this one is not orthogonal. You need to time some inverse sharp power form when you do this spectrum resolution, and this inverse sharp power form kill this sharp power form. So it's like basically you only get this dedekind eta function which counts the dimension of each descendant, each fixed level descendant space. Okay, this is a part of book.
So the eta function is P independent, right?
The P infinite, it only depends on modulus. I can also either right here or here.
But also, the little pictures in that formula, your G mu is just this circle with puncture and one boundary point. So there's probably some picture explanation why you get this formula, right?
Might be. Okay. Now I go to the.
Yes, it's because when you cut, you glue a disc with insertion in the middle, no? So this is where the G is coming from.
Yes, I mentioned here, this is the eigenstate. So for the primary eigenstate, maybe I write another proposition. These two combined together give you a result. This one. If you're pairing with eigenstate, let's say just the Q plus idea fixed on the spectrum. If you're pairing this with this, you get some simple Q factor times the G mu B1 Q plus idea gamma. The gamma appear because here I weighted some boundary GMC measure on the outer bound. This one helps you compute the primary pairing. For the descendant pairing, you just need to compute what will change by this kind of Virasara action. And this can be computed by using some deformation use some full deformation or some variation of Liouville amplitudes, which I didn't introduce very carefully here. But you can compute this.
But in that formula is gamma, you have alpha, beta. Beta is what you put in this cross on the boundary.
Yes.
So this in your formula is gamma. So how do you see this?
Here, you can imagine I uniformly on this boundary mark a gamma over 2 insertion. Because I weighted by boundary GMC measure. If you look at this formula, this is the boundary GMC measure. It looks like you weighted, you have some boundary insertion gamma, but you weighted at every point on this outer boundary. Okay. How many minutes?
0. How much time do you need?
I don't know. Maybe I just stop here.
If you need 2 minutes to wrap up, I don't know.
I think it's not possible to expand the whole proof, but maybe if control is interesting, I can expand to you how to prove the why this 3-point function is related to the 6G symbol, something like this, or model kernel. Okay.
You are not going to complete the table?
I think to complete this will take some time.
I think you should try to use 2 minutes to see how much you can cover. Without writing.
Maybe the formula finish the lecture and then he can continue to those who still have time.
Maybe I can I just complete, and let me try to complete this within like several minutes. So here, this is for the bulk bootstrap. Remember, in the bulk bootstrap, we cut some circle, and for the boundary bootstrap, we cut along some arcs. So here we need the coordinate space should be some field live on the half circle, but we plan to view this as some even functions on the whole circle. We consider this as the coordinate space is just HS even, and the phi tilde h. H means the half circle here. Like so, coordinate space is given by c plus phi equal c plus sigma phi and h. Now here, since the function is even, I have this kind of condition, like the positive n equal the coefficient of negative n. This is the coordinate space, and the Hilbert space is given by the with some measure d mu 0 plus. Basically, you want to make this phi n h as some real Gaussian. This is some real Gaussian. And for the spectrum resolution, let me first say the Hamiltonian and the eigenstate in this case. The Hamiltonian correspond to some amplitude which has some Dirichlet marking here, and here I need to input some field phi. The Hamiltonian is like this one. Here I put some Newman boundary here, and I put some Newman boundary condition. This is the Hamiltonian. And the eigenstate, so I only keep a picture like the boundary case. The eigenstate correspond to there is a insertion here, and you consider this kind of amplitude. And on two sides, you have two boundary cosmological constant. And when you define the amplitude, you need to introduce some Gaussian free field, and the Gaussian free field you choose is here is the Dirichlet boundary condition and the Newman boundary condition here. And this is we call the H plus. And for the eigenstate, we call the psi beta. For the primary one, correspond to this half disk. Compared here is like a whole disk, but here is a half disk. And this one corresponds to some half anyline. And the eigenstate is given by, you can also study the spectrum properties of this H plus, and the eigenstate is given by this. There is only one Wilson algebra here. And the eigenstate depend on mu and mu b1, mu b2. This is the eigenstate. Now use this eigenstate, you can diagonalize the whole space. And maybe in next 3 minutes, I explain why the fusion kernel is related to the boundary 3-point function.
Can you just finish the lecture formally and let the speaker continue?
There's something planned for next
There
hour.
is something else planned.
Or maybe I just stop here. I just said in the general picture, you have some cutting. Once you cut once you cut an arc, you use this kind of spectrum resolution and do this kind of word identity. And if you cut some circle, maybe there are some insertion here. And if you cut some circle, you use this kind of Bootstrap and compute the Watt coefficient. And you collect all these Watt coefficient and do the summation over the Young diagram, you will get the conformal block. And the thing here is because there are some conformal boundary condition, what you get is in the boundary case, the conformal block you get is always the conformal block of each Schottky double. So this is somehow called a Cuddy doubling trick or something known in the physics literature. Maybe I just stop here.
So we're a little bit over time, so is there maybe one short question? None? Okay, let's move on. Thank you. Thank you.
And maybe last, I want to thank all the participants and all the